So, Professor Michel, can we start?
Yes, I think it should be okay.
Okay.
We can try. Yeah.
Okay. So I extend on behalf of the Babu Banarsi Das University and the Mathematics Department, I extend a very warm welcome to all the participants. This is our initiative to reach the general public and especially the students and the people interested in mathematics. We are going to touch upon certain topics in this lecture series, which are usually untouched because of the heavy load of teachings during the semester. And we have five very renowned speakers in this series. Today is the first talk by Professor Michel Waldschmidt. He is a member of Sorbonne University Institute of Mathematics, France, and he is supposed to be one of the experts in the world on transcendental numbers and Diophantine equations, and he has been the president of French Mathematical Society and is associated with many other mathematical bodies and societies such as American Mathematical Society, European Mathematical Society, SIAM, International Mathematical Union, Society for Spatial Functions and Applications, and Ramanujan Mathematical Society. He has also been the president of International Center for Pure and Applied Mathematics, SIMPA, at Nice, and he has published more than 200 papers, and he has lectured in 70 countries in different universities, is on the editorial board of the most prestigious mathematics journals of the world, and he has produced around 22 research scholars. And if you look at the Mathematical Genealogy Project of American Mathematical Society, you can find his 108 descendants, and one of the mathematical ancestor of Professor Michel is Leonard Euler. So we are proud to have him with us, and it's my pleasure to be associated with him, Professor Michel. It's a pleasure for me to associate it with you since last few years, and I'm thankful to you for accepting this invitation, and I'm sure that with your expertization and the participants will be benefited a lot, and especially the students of mathematics who are joining us will take a special interest in the subject and will carry it ahead as their future, as their career. Thank you very much. So I'll request Professor Michel to start your lecture. Thank you.
So, thank you very much for this very kind presentation. I am very glad and proud to be the first speaker of this very interesting series. Congratulations for launching such a series. Before I share my screen, I would like to show you something about the topic of my talk. I will start by speaking of the format of the paper, which is called A4. This is the most classical format. I have a paper which is of the A4 size that you see here. And there are some very interesting mathematical properties of this paper. The first one is that if you cut it into parts, you split it into two parts, you have two papers which have the same proportion as the big one. How do you check that the two papers, the small one and the big one, have the same proportion? You just put them in perspective, and the small one will just hide the big one. And this means that they are proportional. And so this is called A4, and the small one is called A5. Now you can do the opposite. You can take two A4 papers and put them one next to the other. And what
So
you get
Michel,
with this
Professor
is
Michel,
the
I
paper.
missed to mention one thing.
Yes.
I'm extremely sorry for interruption.
No, no.
I missed to mention one thing to all the participants. If you have any question, Professor Michel has kindly agreed to answer your questions also. If you have any question, please type it in the chat, and at the end, some of the question will be put before him to answer. Thank you. You can go ahead.
Okay, thank you. So I was just saying that if you take two A4 papers and you put them together, you get what is called the A3 paper, which is twice the same size. And if you take two A3 paper, you get A2 paper, which is still bigger. So this is in fact from the SIMPA website. I suppose that some of you know what is the SIMPA. You can look more closely here. The SIMPA is an organism which takes care of schools. And okay, so these are the SIMPA schools. Anyway, so this is the property of the A4 paper. When you cut it in two parts, you get a rectangle which has the same proportion. And we will see what is this proportion. So this is one of the explanations which I will start with. The second one is the following.
Yes.
Again, I start with the A4 paper, but I remove a square. So if I remove a square, to remove the square, you know how you do it. You just fold it in such a way that here you have a square. So if you fold it like this, you get a small, well, a rectangle here, which is this rectangle here. So let me take this rectangle here. So this is the small rectangle. From this rectangle, you can repeat the same process and remove one square. But if you remove one square, you see that you have a rectangle which has, again, one square that you can remove. So you remove it, and you have a very tiny rectangle, which is this one. So this is the small rectangle. And if you remember that we started with a bigger rectangle, you can see that the two rectangles have the same proportion. If you look like them, like this, if you put them in perspective, the small one just hides the big one. So I will explain what is going on, and you will see that there is some very interesting mathematics behind this. So let me try to share the screen now. Okay, so is it okay like this? Can you see my screen? Do you see my screen?
Yes, sir. Yes, sir.
Yes, sir, yes.
Okay. So I am going to speak of the square root of 2, the golden ratio, and the Fibonacci sequence. The abstract, which I have sent, I think, is that the square root of 2 and the golden ratio are two irrational numbers with remarkable properties. Irrational means that they cannot be written as the quotient of two integers. They cannot be written a over b when a and b are integers. And I will prove this, that they cannot be written a over b. The Fibonacci sequence, 0, 1, 1, 2, 3, 5, 8, occurs in many situations in mathematics, as well as in the real life, and I will review some of these properties. So I don't know why there are these things, but let us forget about it. Do you have some straight line, like some line like this? Okay, anyway, I don't know what it is. The number square root of 2 occurs in very ancient mathematical documents. One of the first is a Babylonian clay tablet, which has something written here, you see. What is written here has been translated as being a sexagesimal number. So 6 decimal digits mean that it is in basis 60, like if it were 1 hour, 24 minutes, 51 seconds. So if you convert this number into decimal places, you get the number 1, 4, 1, 4, 2, 1, 2, and so on, which is a very good approximation to the number square root of 2. And this is not a coincidence, because if you look here, this is a square, and we look at the diagonal of the square. So this is a very old number. And the A4 paper that I mentioned before is the paper which is called sometimes 21 times 29.7. This is the number of centimeters of the two sides of the paper. And what I will call the ratio, the proportion of the A4 paper, is 297 divided by 210. You can divide by 3, and you get 99 divided by 70. And this number is 1.41428, which is close to square root of 2. I would like to point out that if you look at this decimal expansion, you find the 14285.7, 14285.7, 14285.7. It repeats always. So it is what we call periodic. More precisely, it is ultimately periodic. Because at the beginning, it's not periodic. You see the 1414, we do not find it later. We find only after 14, and then 27. But for the number square root of 2, it's not periodic. You get a sequence which is, we know that it is not periodic. So it seems that there are some people with the microphone on. It would be better that you put it on the silent mode, please. Thank you. So A4, the letter A, is one of the sequence of papers, but there are other formats which are B and C, and all these formats have the property that if you split the paper of A, B, or C format into two parts, you get two rectangles with the same proportion. So there are some sign which occurs in my slides. I don't know why, but let us forget this. I don't know what is that. So if you take a large rectangle where the sides are X for this one and 1, and if you cut it in two parts here in the middle, you have a large rectangle with a proportion X divided by 1, and a small rectangle with a proportion which is 1 divided by X over 2. So the first has the proportion X, the second the proportion 2 over X. And if you want the proportion to be the same, it means that X is equal to 2 over X, which means that X squared is equal to 2. And so this is the square root of 2.
Step number 6.
If you take the large rectangle and the small one, they are proportional, which means that if you look at them from here, you see that the small one just hides the big one. And this can be seen also on this picture. If you put the big rectangle here and the small one there, which is just half of the big one, the 2 points C and C prime are on the straight line with the point O. So this means that the proportion is the same. The number square root of 2 is twice its inverse, which is square root of 2 equal 2 divided by square root of 2. If you fold a rectangular piece of paper with side proportion square root of 2, you get a new rectangular piece of paper with the same proportion square root of 2. And so the definition of the A format is that you start with A0, which has an area of 1 square meter. And because of that, the size will be 118.9 centimeters for the long one and 84.1 for the small one. And the product will just give 1 square meter. For the BSC format, the idea is the same. It's only the start which is different. For the B format, the B0 is 1 meter times 1.414. And so this is the B0 format. The main point is that you start with 1, and then you divide by 2 successively. For the C format, you start with the size, which is 917 millimeters and 1,297 millimeters, which is essentially 1 over 8 root of 2 times the 8th root of 8. So this is the B and C format. So I would like to remove that, but I don't know What is this arrow? Anyway, so let us start with this format, which is the A4 format. A4 format is 21 times 29.7. If you put two papers of A4 format, one next to the other, you get the small size, which is 29.7, and the large, which is 42. So it gives a A3 paper. If you double the A3 paper, as I showed before, you get the small size, which is 42, and the big, which is 59.4, which is twice this one. And you give the A2 format, which was the format of the SIMPA website. And then when you double and you double, you get the A0, which is x1, x2. So this is it. You have x1, x1 over 2, x1 over 2, x1 over 4, x1 over 4, x1 over 8, and so on. So this is sufficient to prove the irrationality of the square root of 2. And let me give the proof, the proof along these lines. You start from two integers, a and b, and you assume that a over b is square root of 2, and you will see that this is not possible. So if you can write square root of 2 as a quotient of two integers, you take a and b, which are the smallest one. So you cannot simplify this fraction. And then you look at this rectangle here, which has the size here, the small size, which is a, and the big size, the small size is, well, the big size is 2b here. This is the large rectangle. And so inside, you put the rectangle, which is a and b, which is just half of the big one. So as I told you, this line is a straight line, which goes through this corner here. If you compute what is a prime is 2b minus a. This is written here. If you compute what is b prime is a minus b. And now the proportion of this small rectangle is the same as the big one, which means that we had a square equal to b square, because of that, but we have also a prime square equal to b prime square. But a prime is less than a and b prime is less than b. So we get a contradiction with the fact that we started with the smallest way of writing square root of 2 as a over b. There are many other proofs of the irrationality of square root of 2. Here is another proof. You assume that a square is equal to 2b square, and you take two squares, one which has the area a square, which is a big one, and you take two small squares of area which is b square. So the green, if you take some painting, for example, you have some green painting and some yellow painting, and the green one is just the same as the sum of the two small ones. And now these two small squares, which are yellow, you put them one here and one there. And again, you paint. So you paint what is here, you paint what is there, and what is remaining is just the red square, which is here. And if you look at what painting is remaining, the painting which is remaining is just this square, but it's also the sum of the two green ones. So this small square, red, is the sum of the two green square which are there. But again, you get the same kind of contradiction. The area of the two squares of side b prime, which are not covered, is the area of the red square. And therefore, you have a prime less than a, b prime less than b, with again a prime square equal to b prime square. So you can repeat with the red square and the green square what you did before. And this is not possible if you start with a minimal expression. Okay, so this is what I told you to start with by folding the A4 paper in two parts. Now, I showed you something else with the A4 paper. What I did was to remove a square from the rectangle with the proportion square root of 2. So maybe I will try to remove this ugly things. So let me hide like this and come back. No, it's still there. So I will start again. Okay, so I suppose you should see my slides again and without this ugly thing. Is it okay? Hello? Is it okay?
Sir. Yes, sir. Yes, sir.
Okay,
Yes,
so
sir.
I think it's better. I don't know why they were this drawing on my pictures. So if you start with a rectangle with the proportion square root of 2, I prefer, in fact, well, you start with a rectangle with proportion to square root of 2, and then you remove one square. This is what I did before. Okay, again, there are some things that I don't know what it is. So you remove one square. And what I showed you is that you get a rectangle here for which you can remove two squares now, not one, but two. And then you get a small rectangle, and this small rectangle has the same proportion as the one that you had here, which means that you can remove two squares and get another rectangle with the same proportion. And because the proportion is always the same, you can continue infinitely often. So what does it mean? It means that you start from square root of 2, which is this number. You remove 1. And so what you have is this length here, which is 1 over 1 plus square root of 2. Because square root of 2 minus 1 is the same as 1 over 1 plus square root of 2. And so this, the proportion of this rectangle, the long one here, is 1 plus square root of 2. And so 1 plus square root of 2, you can remove two squares, which are these ones, and you get another tiny rectangle, which is this one, which has the proportion 1 plus square root of 2. So it's the same proportion again. So if you continue this process, you see that it will never stop. It continues forever. Now, if you start with some rational numbers, I take 99 over 70 because this is the same as 297 divided by 210. And I will prove that this number is not square root of 2, but you can take two numbers A and B and get the same conclusion. So if you start with this rectangle, which has the size 99 and 70, you remove a square. The square that you remove, the size is 70. So what you get here is 29. It is 99 minus 70. So this is 29. And of course, this has not changed. It is 70. Now, from this rectangle here, you remove twice 29, which is this one. So you remove it twice, and you get this rectangle here, which is 29, 12. And now, from this rectangle, you remove twice 12, which is here, and you get this point here, which is 5, 12. You remove again two squares, you get 5, 2, which is here. You remove two squares, you get 1, 2, and then it stops. And it should stop just because you always have integers here, and the integers are decreasing, so the sequence is to be finite. And so if you start with any two integers, the sequence will be finite, and so the quotient will not be the square root of 2. What I just explained here by writing this number as 1 plus a number, you take the inverse of this number, you write it twice plus a number, you take the inverse, you write it twice plus a number, and so on. This is the so-called continued fraction algorithm. You start from this number, square root of 2. It satisfies square root of 2 equal 1 plus 1 over 1 plus square root of 2. And this square root of 2 here, you replace it by the value which is given here. So you get 1 plus 1 over 1 plus, and then 1 plus 1 over 1 plus square root of 2. So this is what you get. And then this square root of 2, again, you replace it with the same formula. And you see that you will have 1, and then 2, 2, 2, 2, 2. This sequence of 2 corresponds to the number of squares that you can remove. It will be more convenient to write it as 1 and 2 horizontally, like this, 2, 2, 2, which means that. And we even use a simplified notation by putting 2 with a bar, which means that we repeat the 2 infinitely often. So 1, 2 bar means discontinued fraction. In the A4 format, what we did just before is to write the continued fraction of 297 over 210, which is the same as 99 divided by 70. And the continued fraction is finite. It stops. You have 5 2's, but then you have nothing. So you have no more squares. Well, the last one is just 2 squares. I will give an application of this continued fraction algorithm by speaking of a puzzle which was considered by Mahalanobis, and then Mahalanobis mentioned it to Ramanujan, and Ramanujan solved it very fast. So the puzzle is about a street in the town of Louvain, Belgium. They said that the houses are numbered consecutively. I think it's just for the puzzle that they say that, because I have been in Louvain and the houses are not numbered consecutively. And in particular, there is not such a street with a number of houses which is more than 50, but it's just for the puzzle. So one of the house has the peculiar property that the total of the number of the numbers lower than it was exactly equal to the total of numbers above it. And the mysterious house number was greater than 50, but not less than 500. So there are some examples, but the examples will not meet the condition that it is between 50 and less than 500. I assume that in the street, you have 8 houses, and you look at the number 6, the house with number 6. On one side, you have the houses with the numbers 1, 2, 3, 4, 5. The total of it is 15. On the other side, you have 7 plus 8. The total is 15, and it is the same. So this is an example. Another example is a street with 49 houses, and you look at the house number 35. On one side, you have 1 plus 2 plus 35, which is 595. On the other side, you have 36 plus 49, and the total is 595. And you see that it is the same. But it does not answer the question because the house number is between 50 and 500. Nevertheless, it's interesting to look at these special examples, because you see that we have to count on one side the sum 1 plus 2 plus 3 plus the number of one side, the small number. And on the other hand, you have to count this sum here. And to count this sum, what you do is that you count the sum from 1 to 49, and you remove the sum from 1 to 35. And so you get this difference, and this difference should be equal to the first number. Okay, so there is another solution which may be interesting to consider, which is a street with no house, and the number of the house is 0. And you have no house on one side, no house on the other, and the sum is 0. And I wish to consider also this solution as the first trivial solution, because this reminds me of Ramanujan when he was a student. The professor said that if you distribute some banana to some students, each student gets a banana. And Ramanujan asked, if no banana is distributed to no student, will each student get a banana? So it's similar with the number 0 in the street with no house. Okay, let me call M the house number and N the number of houses. So on one side, you have 1 plus 2 plus 3 plus M minus 1. On the other side, you have M plus 1 plus M plus 2 plus N. So what you have to solve is M times M minus 1 over 2 equal N times N plus 1 over 2 minus M times M plus 1 over 2. On the right side, you write the numbers, the sum from 1 to N, and you remove the sum from 1 to M. So this is what you have to solve. You simplify, and you find that you have M squared over 2 here. You have minus M squared over 2, which goes on the other side. You multiply by 2. and you get 2n squared equal n plus 1. So you complete the square when you have a quadratic equation like this. The n plus 1, you write it as a square. It is the square of n plus 1/2, but you multiply by 2. You multiply by 4, in fact. So this gives 8n squared, which is 2n plus 1 square minus 1. And you see that if you replace x by 2n plus 1 and y by 2m, you have to solve x squared minus 2y squared equal 1. And conversely, if you have a solution of x squared minus 2y squared equal 1, you see that x should be odd, because you have 2 here and 1 there. X should be odd, so you can write it 2n plus 1. And then when you have x, which is 2n plus 1, you deduce that y should be even, and then you get the equation which is here. So it's really the same to look at this equation which is there. Okay, so we have to solve the equation x squared minus 2y squared equal 1. X is 2n plus 1, y is 2n. There are several ways of solving this equation. I give the first way, which is to use the square root of 2, because this is what we are going to speak about. And you write x squared minus 2y squared equal x minus y square root of 2, x plus y square root of 2. There is a trivial solution, which corresponds to no house and the number is 0. You take x equal 1 and y equals 0, and you see that this difference is equal to 1. But we want non-trivial solution, and there is one which is obvious, which is 9 minus 8 equal 1. This means that you take x1 equal 3, you will get 3 squared, y1 equal 2, you get 8, and the difference is 1. With this equation, once you have a solution, you deduce all the other solutions by taking the coefficient, the factor x minus y square root of 2, and taking powers of it. So if you take the square of x minus y square root of 2, with 3 and minus 2, if you take the first power, you give the previous solution. If you take the second power, you get 17 minus 12 square root of 2. This is 3 minus 2 square root of 2 square. And this gives 17 and 12. And for the number of houses, it's 8. And for the number of the house, it's 6. And this is the solution that we found before. If you take the cube, you get 99 and 70. And this gives the house number 35 in a street with 49 houses. I would like to point out that when you have 99 and 70, if you look at 99 divided by 70, this is the same as the A4 format that we have seen before, 297 divided by 210. And it's not a coincidence, it's closely related. So this street with 49 houses and the number of the houses 35 is related with the A4 format. This kind of equation was considered by Brahmagupta in 628. And one nice example of Brahmagupta was instead of 2, he had 92 here, x squared minus 92 y squared equal 1. And he gave the smallest solution. There is no smaller solution than that. And the solution that he gave is x is 1151 and y is 120. The way that Brahmagupta did it is not exactly the continued fraction, but it's something which is very close to continued fraction. What he did is to write the continued fraction expansion of square root of 2. This continued fraction expansion starts with 9. Then you have 1, 1, 2, 4, 2, 1, 1, 18. And after that, it repeats. It is 1, 1, 2, 4, 2, 1, 1, 18, and so on. So it's always the same pattern. So it's a periodic continued fraction. And if you omit the 18, and if you look at this continued fraction, which is here, you get a rational number because it's a finite continued fraction. And you check that this gives a solution xy. And you see this approach to the equation x squared minus 2y squared equal 1 is probably the one that Ramanujan had in mind when he solved the puzzle. Bhaskara continued the work of Brahmagupta. He used the so-called cyclic method or Chakravala of Brahmagupta, and he solved a much more difficult equation, which is x squared minus 61y squared equal 1. It's much more difficult because the smallest solution has many digits. It is this number, the smallest solution. But the method is the same. You write the square root of 61, you write the continued fraction expansion. It is much longer here. It goes up to 14. And it's a little bit more difficult here. What you have to go is to repeat this period here. So you repeat it there up to 14. And then you continue up to 4, 1, which is there. So 3, 4, 1. 4, 1 is the same as 5. And then you get this number. So this was the method of Bhaskara. So let us do that with our simple example. And our simple example is x squared minus 2y squared. So we have the first non-trivial solution, which is obtained by 3 over 2, 1 plus 1 over 2. The second solution is obtained by writing the continuous fraction expansion 1, 2, 2, 2, and we stop here. And so we have 1 plus 1 over 2 plus 1 over 2 plus 1 over 2. And when you compute it, you find 17 over 12. And this gives the second solution. If you write the next solution, 1, 2, 2, 2, 2, 2, then you get 99 over 70. This is something that we have seen before. And this gives the next solution. And so I told you this is not the solution that was asked by the puzzle, but now we look at the fourth solution. And the fourth solution is given by taking some more 2, which are here. You get this continuous fraction expansion, which is finite. You get 577 over 408. And then you deduce that this is a solution xy, but you have to convert for the house number and the number of houses in the street. And the final answer to this puzzle is that the house number is 204, and the number of houses in the street is 288. And indeed, if you count the sum from 1 to 203, you find 20,706. And if you count the sum from 205 to 288, you get the same number. So this is the solution of the puzzle. Now, it requires some computation to do that, but it's possible to go faster to find this solution. And we do not know whether this is what Ramanujan did. We can ask for the next solution, because the question was the number of the house, which is between 50 and 500. So we have to check that there is no solution other than the one which I just showed. And indeed, the number of the houses, the possible numbers, are 1, 6, 35, 204, and then it is 1,189. So it's more than 1,000. And the number of houses in the street is given by these numbers which are here. And how do we go from one number to the next one? It is a so-called linear recurrence sequence, which means that if you know 2 consecutive numbers, you get the next one by multiplying this one by 6, and then you remove the previous one. So if you want this number here, you multiply this one by 6, you remove this one, and you get that. So this is a very simple way of doing it. It is a so-called linear recurrence sequence. And it's likely that Ramanujan knew that and could compute very easily the sequence of number of the houses. If you want to know more about that, I advise you to look at the online encyclopedia of integer sequences by Sloan. And on this encyclopedia, you will find a lot of information. The database is very complete, and it's very useful. I use it myself for my research very often. I mentioned the decimals of square root of 2. It starts with 1.4142135 and so on. And I give here a few decimals that you can compute easily. and you do not see any pattern. And this is the main point. In the continued fraction of square root of 2, the pattern is very clear. It's 2, 2, 2, 2. It's periodic. But for the decimal expansion, we do not see any pattern. Instead of the decimal expansion, you can look at the binary digit. And again, you have a sequence. Now it's the digits are 0 and 1. You have a sequence of 0 and 1. And in fact, you can safely use it as a random sequence. And this is a conjecture. We expect that the two sequences behave like random sequences. A number of decimals of square root of 2 has been computed. In 1951, before the computers, Euler computed more than 1,000 digits. But then with the computers, it's possible to get a very large number of digits. And one reason to compute these digits is that the square root of 2, the computation of square root of 2 occurs in the computation of pi. So if we want to know the decimals of pi, we need to know the decimals of square root of 2. Borel considered this sequence of decimals and binary digits, and he made some very interesting conjectures, which are still conjectures nowadays. And I would just say that he expects that these two sequences, binary digits or decimal digits, behave like random sequences. He puts this in a very precise mathematical way, but I will just give one precise open problem. You choose one digit, the one that you want, between 0 and 9. You choose a real algebraic number, alpha, for example, square root of 2, but you can take any algebraic irrational number. So it's a root of an equation. It could be the cube root of 2 or something like this. And it is algebraic. It's a root of an equation, and it's a real number. So the question is it true that the digit C occurs infinitely often in the decimal expansion of alpha? And the conjecture is that the answer is always yes. And the fact is that there is not a single example where we can prove that it is true. For example, you take square root of 2 and the digit 7 in basis 10, but you take any algebraic irrational number, we do not know one digit which occurs often, infinitely often. Of course, there are some digits which occur infinitely often, but we do not know to give one precise example. So this is an example of an open problem, which is very challenging. There has been some progress during the last 20 years, say, but still this problem is open. Okay, I spent almost all my time on square root of 2, and I am supposed to speak also on the golden rectangle and the Fibonacci sequence and the golden ratio. So I will start with now with the golden rectangle, and I will give the definition of what is a nice rectangle. So this is a nice rectangle. And what is the definition of a nice rectangle? The nice rectangle is that if you remove a square, you get a smaller rectangle, so the dark blue here, which is again a nice rectangle. So I like to take the definition inside the definition, but it makes sense. So you take a large rectangle, the size are 5 and 1, you remove one square, so the small rectangle has the size which are 1 here and 5 minus 1 here. And so the big rectangle has the proportion 5, and the small rectangle has the proportion y, 1 divided by 5 minus 1. So this is what we have. This number 5 satisfies 5 over 1, which is 5, is equal to 1 over 5 minus 1. So this is 5 squared minus 5 equal 1. And this is the number 1 plus square root of 5 over 2. So a golden rectangle is a rectangle where the proportion is 1 plus square root of 5 over 2. So again, we can write the decimal expansion, 1, 6, 1, 8, 0, 3, 3, and so on. As I just mentioned, we do not know single digits. We cannot name a digit which occurs infinitely often. Of course, there are at least 2 digits which occur infinitely often, but we do not know one. So this number satisfies 5 equal 1 plus 1 over 5. This 5 here, I replace it by 1 plus 1 over 5. And therefore, the continued fraction expansion of phi is 1, 1, 1, 1, always 1. And if you remember how I defined the continued fraction, it means that if we start from a rectangle with the golden ratio as proportion of side length, at each step, we get a square and a smaller rectangle with the same proportion for the side length. So when we split the golden rectangle into a square and a small rectangle, this process will continue forever. And this is the proof that phi is an irrational number. And from that, you deduce that square root of phi also is an irrational number. So this is what you get. You get the golden rectangle. The long size is 5. The small size is 1. You remove 1 square. You get another rectangle. And the size are 1 here and 1 over 5, which means that the ratio is 1 over 5. So we start from the big one to the small one by taking homothétie, as we say, of radius 1 over 5. So if we repeat it, we get 1 over 5 square because we multiply by 1 over 5. So this rectangle here is 1 over 5, 1 over 5 square. And of course, the ratio is 5. And then you have 1 over 5 cube, 1 over 5 to the 4, and so on. So this is the golden ratio. You have a lot of common properties of similarity between the golden number, the golden ratio, and the number 1 plus square root of 2. In one case, you have the continued fraction, which is only with 1. In the second case, you have the golden, the continued fraction, which has only 2s. So one example is that the golden ratio occurs in the diagonal of the pentagon. You take a pentagon, so the pentagon, which I consider is the small one, which is here. Do you see it? Yeah? Okay, so this pentagon has one diagonal, phi. You have another diagonal which has the same size. So let me take this diagonal here, which is phi. And now the property is the following. I name it phi, and I will check that phi is a golden ratio. What you do is that you continue this line here with the length 5. And you continue this line, you add 5 again here. And so you will see that they meet at this point, which is here. It's just an exercise of geometry. And then when you look at this pentagon, which is here, this pentagon is has the size which is 5. So it is obtained from the small one by enlarging by a ratio which is 5. And so the diagonal which is here is 5 plus 1, but it is also 5 square because we multiply 5 by 5. So it's 5 square. So this gives 5 square equal 5 plus 1. And you can do the same with the diagonal of the octagon. It is 1 plus square root of 2. Here you have square root of 2 over 2. Here you have square root of 2 over 2, and you have 1. So the diagonal of the octagon is 1 plus square root of 2. Another similarity, you can write phi square equal 1 plus phi as phi is the square root of 1 plus phi. And again, this phi here, you replace it by the square root of 1 plus phi, and you can continue and you get this, which is called the nested root, square root of 1 plus square root of 1, and so on. You may have heard of nested root because there were some exercises, some problems in the Journal of the Indian Mathematical Society in 1912, which were solved by Ramanujan. The first one was to know what is the value of the square root of 1 plus 2, square root of 1 plus 3, square root of 1, and so on. And Ramanujan gave the solution, which is 3. And the other exercise was with 6, 2, 7, 3, 8, 4, 9, and the answer is 4. And you can do the same with the square root of 2. You can write that 1 plus square root of 2 is the square root of 1 plus 2 square root of 1 plus 2 square root of, and so on. So you see, it's very similar to the golden ratio. I will just finish with the Fibonacci sequence because this was part of my title. You start with the question of knowing how many ancestors do we have. So we have 2 parents. Each of the parents have 2 parents, and each of them has 2 parents. And you get the sequence 1, 2, 4, 8, 16, which is the so-called geometric series, as it is written here. So un is 2 to the n, starting with u0, which is 1, which is this unique people. This genealogy is not true for all beings. If you look at the bees genealogy, the male honeybees are born from unfertilized eggs. The female honeybees are born from fertilized egg, which means that males have only one mother, they have no father, but the females have both a mother and a father. So this is a male, he has a mother, the mother has a father and a mother, the father has only a mother, and the mother has a father and a mother, and so on. And you count how many ancestors does it give. And if you count the number of bees, you get 1, 1, 2, 3, 5, the total number. The number of female is 1, 0, 1, 1, 2, 3. And you see that after that, it will be the same sequence as this one. And the rule is un plus 2 equal un plus 1 plus un. So it's different from the genealogy of human beings. And if you look at these numbers, you start with one male, one female, one male and one female, and you continue like this, and you get the sequence, which is 1, 1, 2, 3, 5, 8 for the total number of bees. And for the numbers of male or number of female, it is the same, which is with some, so you just split, you just start from 0 here and here. The sequence which I just mentioned, 0, 1, 2, 3, 5, 8, was called the Llama Series during some time because Gabriel Llama used it to give an upper bound for the number of steps in the Euclidean algorithm for the greatest common divisor. But after that, when Edouard Lucas went to Italy in 1876, he found a copy of this sequence in the Libera Bacci of Leonardo da Pisa. And Leonardo da Pisa studied this sequence, which is now called the Fibonacci sequence. And this is his book, Liber Abaci. Again, of course, you find this sequence in the Encyclopedia of Integer Sequences. And Fibonacci introduced this by considering the growth of a rabbit population. And he started with a new born pair of rabbits, which is a male and a female. So what he counts is the number of pairs of rabbits. And we looking at the number of descendants, he got this Fibonacci sequence. Maybe my time is almost over, so I will not give too much detail about that. I would just like to continue by, so this is the connection with the golden ratio, but you can find my slides on my website. But I would like to, so there are a lot of things to say on the golden ratio and the Fibonacci sequence. And so I will not explain all that, but you can look at it on my website, and you will see that there are a lot of very interesting mathematical properties. I would like just to conclude by saying that this sequence of Fibonacci is not the first one which occurs as a linear recurrent sequence, as I mentioned it before, in the mathematical literature, because Narayana was an Indian mathematician in the 14th century who proposed the following problem. A cow produces one calf every year. Beginning in its 4th year, each calf produces one calf at the beginning of each year. How many calves are there altogether after, for example, 17 years? And if you look at what it gives, it's very similar to the rabbits of Ramanujan. There is a difference. It is that now it's a Cn plus 3 equals Cn plus 2 plus Cn. You see, this is 3, 2, and n, instead of 2, 1, and n. And so the initial values were 2, 3, and 4, and he gets a sequence which is 2, 3, 4, 6. And this sequence was used in music by Tom Johnson, who make a composition which is called Narayana's Cows. So I think my time is essentially over. I will not, I do not forget that there should be some questions. So I welcome the questions if you have some of them. So thank you for listening.
Thank you, Professor Waldschmidt. Uh, there is one question only from one of the participant. He is Subhajit and his question is there any case of transcendental numbers where it is shown that in its decimal expansion we do get all the digits randomly?
Very good question. Thank you. So the answer is yes. If you fix the basis 10, so you mentioned the decimal expansion, there are many examples which are known like this, and of course you have to define what means randomly. So there are several examples like this, and one example is if you take the number which is the following: 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then you continue, you write 1, 0, 1, 1, 1, 2, and so on. So you may say that it's not really random, but it has the property which was asked by Borel, which means that if you take any sequence of digits, it will occur infinitely often in this decimal expansion. So it satisfies some of the properties of a random sequence. You see, if you look at the property that you can ask to random sequences, there are many properties that you can ask, but there is not a single number which satisfies all these properties. It's something which is not difficult to prove because there are too many properties which are satisfied by a purely random sequence. So there are several other examples which are known. And so the answer to the question is yes, there are some examples. If you want to have some references, you can find my email address, and you can write me, and I will send you some reference.
There is another question from Guru Prasad. Is there any progress in Borel's conjecture that you have mentioned in the present lecture?
Yes, so I can say what is the progress which has been made. It is in the theory of automata. What has been proved by Bugeaud and Adamczewski less than 20 years ago is that an automaton, finite automaton, cannot produce an algebraic irrational number. It can produce either a transcendental number or a rational number, but not an algebraic irrational number. So I should define what is an automaton. It's a little bit complicated, but it means that there is no very simple computer process to produce the decimal expansion of an algebraic number.
I think there is no other question. There is one more question many people asked, and yeah, there is another question I have got. Is Fibonacci series observed in astronomy?
I would like to emphasize the fact that in all the physical aspects, the numbers which occur are not mathematical constants in the sense that they are not defined by equations which gives an exact value from a mathematical sense with infinitely many digits, decimal digits or binary digits. So if you look at any astronomical process, you need only to have some good approximation, but a few decimals are sufficient. So you do not get a transcendental number because a transcendental number involves the fact that you have an infinite sequence. In all the physical processes, what you get is constants which have a good approximation, but not a mathematical definition.
There is another, it seems to be more a comment, not a question. The one equation which you shown in the street number example is the type of Pele's equation?
A type of periodic? Well, what happens is that in the equation which I gave, it was x squared minus d y squared equal 1.
The question which is someone is asking, uh, the one equation which you shown in the street number example is the type of Pell's equation?
Yes, yes. I did not use the name Pell. In fact,
Yeah. Okay.
this equation is named Pell, but we know that it was a mistake by Euler who used the name of Pell, and Pell never worked on this equation. Now, when I give a talk about that, I speak of the Ramanujan-Fermat-Pell equation. Fermat worked on that. Ramanujan was the first to work on that. And Pell is the name which was given by Euler. So I did not use the name Pell, but this is exactly what I was speaking about. It is the so-called Pell equation. This is correct.
Yeah, there is another question. What is the difference between golden ratio and metallic ratio? What is the difference? What is the difference between golden ratio and metallic ratio?
Okay, there are a number of constants which have a name, and there is a silver ratio and so on. And each time it corresponds to a different equation. So the golden ratio is the equation x squared minus x minus 1 equals 0. So it's a polynomial x squared minus x minus 1, and we look at the root. And there are a number of other constants which are real roots of such polynomials. So there are plenty of names. I don't know exactly what is a metallic, but I know that there is a silver and there is well, there are many names like this.
Someone is asking, does Narayanan sequence follow rectangle ratio?
Oh, I did not understand the question.
Does Narayana
Narayana,
sequence,
yes.
yeah, sequence follow rectangle ratio? This question is not clear, I guess.
Yes, the Narayana sequence, does it follow which? So the Narayana sequence says I have displayed what is the root of the equation, which correspond. And this root of the equation is a cubic root. So it has a continuous fraction expansion, which is not periodic. We know that it's infinite and not periodic, but we do not know much about that. So we do not know whether the integers which occur, which correspond to the number of squares, are bounded or not. We expect that they are not bounded, but we do not know. So there are still some mysterious facts about all the equations which are not quadratic. When it is quadratic, the theory is rather complete. When it is not quadratic, like for this equation with Narayana, then it's much more difficult.
Another question, is it possible to write every sequence in a rectangle of ratios? Is it possible to write every sequence in a rectangle of ratios? The question is not clear, I guess.
Yes, to write a rectangular, well, any sequence in a rectangular
sequence.
I
think he's not clear, I guess.
Yes, because a sequence, I understand, I suppose it's a sequence of integers, and then you write a sequence of integer in a rectangular fashion. I don't really see what it means. Sorry.
So the question is, does golden ratio really does show up in black hole physics?
Well, I don't know. So some people see the golden ratio in many places where it is not. The golden ratio could occur in physics, not as such, but as approximation of the golden ratio, because it has some interesting properties, like properties of symmetry of order 5. The symmetry of order 5 has an interesting history, because it was known that there is no tessellation which has a symmetry of order 5, and it's only quasi-crystalline tessellation which gives it. So in quasi-crystal theory, it occurs, the golden ratio. in the black hole, this I don't know. It could occur, but I don't have a reference.
There is one question, one more question, sir. The last question, I think it is also not very much clear, but I'll read it. One of the participant has written that I don't logic that if we add all natural numbers, then how we get negative values, that is -1/12.
Okay. So this is a question which I like because
Right.
this is a question related with Ramanujan. Okay,
Yeah,
so there is a very interesting book by Hardy, which is called Divergent Series. Divergent Series. And the introduction of this book by Hardy is very interesting. So if you want to understand something about that, I advise you to look at this book of Hardy. This sum, which is -1/12, was found by Euler, and then it was found by Ramanujan completely independently. And when Ramanujan sent his result to some mathematician in England, they said, this is just nonsense, because they did not know divergent series. And then when Hardy received the letter, he said, oh yes, this is well known. And of course, this is a bit shocking for the students, because we explain what is a convergent series. And Hardy explained quite clearly what is a convergent series in the sense of Cauchy. It's a series which satisfies some properties, and this is the Cauchy property. And we say that the series is convergent if the Cauchy property is satisfied, and then there is a limit, and it is a limit of the partial sums. Now, we often write, for example, 1/2 + 1/4 + 1/8 and so on equal 1. But on one side, we have a formula, a series. On the other side, we have a number, which means equal 1, that the sum is equal to 1. It's an agreement that the mathematicians have after Cauchy, that the left-hand side is a series which satisfies Cauchy's condition, and therefore we attribute to this formula a value, which is the value 1. Now, if the left-hand side does not satisfy Cauchy condition, Cauchy does not give any value. And what some mathematicians have done is to say, okay, we have a series which satisfies some other condition, and we will give a value to this series. And there are several ways of doing that. And of course, a good way is provided that in the case of a convergent series, it gives the same value of as a Cauchy. But in the case of a non-convergent value, non-Cauchy sequence, we give another number, which is defined in several ways. And there are several ways to do that. And the -1/12, there are several ways to get it. But what is important is that it is not the limit of a partial sum. For Cauchy, it is the limit of a partial sum, but not for a divergent series. So it's another definition.
So there is one participant, he wants repeatedly, he is sending this message in the chat, though it is out of the context, but since this is repeatedly, the participant is typing, he wants some comments on Hardy-Ramanujan number.
Oh, which comment does he want?
I mean, sir, the question which is typed here, can you comment on Hardy-Ramanujan numbers? So it's a very open-ended question.
Hardy-Ramanujan numbers, I don't know what he means by Hardy-Ramanujan numbers.
Yeah.
There are a lot of joint work by Hardy and Ramanujan, and they work together. They published a large number of papers. So I don't know whether there is some number or some numbers. I don't know which has the name Hardy-Ramanujan numbers. There are some methods which have been introduced in analytic number theory by both of them, in particular the so-called circle method. And the circle method is very efficient, but...
maybe he meant 1729.
Oh, 1729. Okay.
Might be.
Yes.
Yeah.
Yeah. Okay.
Yeah.
So This number 1729, it's a story which was written by Hardy himself. And there is some doubt that Hardy did not know that 1729 is a very interesting number. When Hardy wrote this story, he wanted to explain, we have to look at the context in which he wrote this story. He wanted to explain that Ramanujan was genius, but his mind was, well, he was not a superstar. He was not able to find things which are divination. And when Hardy tells this story, he completes it by saying that he asked himself to have a number which is the sum of two four square in two different ways. And Ramanujan explained that probably it is a very large number. I don't know exactly. Maybe it was a number of three square in two different ways. Anyway, he asked another question, and the answer of Ramanujan was it must be a very large number. So there are a lot of things which have been written about the fact that it's a taxicab number. What you can do is to look at my website. I just gave a talk on the internet. It's a web seminar, a webinar. I gave it in May, and I mentioned this story of Ramanujan and Hardy visiting Ramanujan, and I give some references to that. In particular, I give a list of links on the so-called Taxicab sequence, and there are several Taxicab sequences. There is the one which is just to find a number which is the sum of two cubes in two different ways, but you can ask a number of other questions similar to this one. And my seminar, the talk which I gave last month is available on the internet. It has been recorded on Zoom. So you can have much more information about that.
Yeah, many people have written about it, and there are other relevance besides some of the two cubes have also been observed about this number. One can search on the net. So I think there is no other question now. So it's time to. There is one question everyone is asking about the website. So you simply type the name Michel Waldschmidt on the Google. You will find thousands of links related to his work, his Wikipedia page, his personal homepage. Lot of information you can find it. So everyone else was asking me. There is another question the people were asking. And I would like to inform everyone that this talk will be available on YouTube channel of the Mathematics Department of the University. So I will share the link of the YouTube link with everyone. So if you want, you can hear this talk again and again, and you can share it with your students also, which will definitely arouse interest in mathematics and a lot of curiosity it will create. So it was a very, and Professor Michel, we have got some very good comments about your session, and it is highly appreciated. And of course, it is very inspirational, very informative, and very motivational. And I'm sure that the people who are attending this and have got a lot of curiosity to explore about square root of 2, Fibonacci sequence, and golden ratio, and related things. A lot of literature is available, and you can find a lot of links from the Michel website also. So I would like to thank Michel for a nice talk, and I think we haven't met from the last 1 year, and I have seen your program sometime in December. So we are also planning the meet in December. We'll get in touch with you
Very
soon.
good. Oh, yeah.
Yeah.
I hope
Depending on the COVID situation. and December first week, hopefully, we are planning at Mysore. You might be knowing.
Yes.
Yeah, this time. So anyway, thank you very much. Thanks everyone, and we will share the link of the YouTube very soon as it is it is available on the website. And I once again thanks Professor Michel for this very informative lecture, and this series will continue. The next lecture will be by Professor Atul Dixit of IIT Gandhinagar on the partition theory, and I hope the people will join. And I will share the meeting link, meeting ID and password one day before the talk. So thank you very much. Thank you.
Thank you, Dr. Ali, for nice lecture.
Thank you. You are most welcome.
Because you are the main person to organize such a wonderful and very informative lecture. So on the behalf of all the faculty of mathematics, I am thankful to you for such a wonderful and informative lecture.
Thank you very much. Thank you very much for joining us.
You have much more information on my website. And in particular, this file is on my website and the address of the website is here.
Right. He has shared his website.
Hello.
Okay.
Hello.
Good. Thank you for your invitation.
Yeah, someone wants to say something.
Thank you.
Thank you everyone.
Thank you, Satan.